Welcome back to the deep dive. Today we're tackling something really fundamental, kind of mind-blowing actually. It's this whole idea of the Goldilocks universe.
Yeah.
The sense that everything around us, the basic rules, the ingredients, they're all set up perfectly, just right, almost. Engineered, you could say, for life to exist. Our mission today is to really dig into this exquisite fine-tuning of the cosmos. We're talking fundamental forces, the masses of tiny particles, even how fast space is expanding. It all seems balanced on a knife edge. Change one tiny thing, and the whole possibility of life, maybe even stable matter, just vanishes. We've looked at a lot of research on this, and honestly, the numbers involved, the precision required. It's hard to wrap your head around. And this isn't just some abstract thought experiment. The core puzzle is very real. Why are these basic settings of reality seemingly dialed in so perfectly if they were off by like a fraction of a percent?
Yeah.
Poof, a sterile universe, instantly. So we'll walk you through some key examples, look at what happens if you tweak the dials, and then get into the big questions it raises. Multiverse, new physics, it's quite a ride.
Yeah, and to really get started, we need to be clear on what we mean by fine-tuning. It's a specific term here. It points to this, well, remarkable precision we see in the fundamental constants of nature, these fixed numbers. But it's not just the constants. It's also about the initial conditions, what the universe was like right at the very beginning after the Big Bang. And when you look at the physics, the argument becomes pretty stark. If you just sort of randomly pick values for these constants, the chances of landing in the incredibly narrow zone that allows for life are, well, statistically vanishing, almost zero. We're talking things like how strong gravity is, or this thing called the cosmological constant. They have to be balanced just so. It's like a cosmic control panel with billions of settings, and only one combination leads to a universe where stars and planets can form. So through this deep dive, we'll look at specific examples of this tuning, the physics behind why it's needed, and then, yeah, the philosophical and scientific debates that spiral out from it. It really forces you to think differently about the universe. Maybe less random chance, more like,
Right.
like a blueprint with incredibly tight tolerances.
Okay, let's try an analogy maybe. The sources use one like baking a cake. Imagine you're baking the universe, right? But the recipe is so sensitive. Ridiculously sensitive. If you add one extra grain of sugar representing, say, the electron's mass, the whole thing either collapses into a black hole or just explodes into useless gas.
That's a good way to put it. And those ingredients are the physical constants. It's really important to grasp that these aren't numbers that come out of our current best theories, like predicting an orbit. Not yet, anyway. They're fundamental values we just
Right.
measure. We observe them in experiments.
Like the strength of gravity, G, or the charge of an electron, we know the number.
Exactly. We know the number, but our current physics doesn't explain why it has that specific number and not some other one. It's just inputted into the equations.
And that's the crux of the fine-tuning argument, isn't it?
Precisely. Because if you imagine these numbers could have been different, if you imagine sort of cosmic factory where universes are made with random settings, then the odds are overwhelmingly against getting one like ours. A universe capable of making stars, stable atoms, things like water, complex chemistry. It's an incredibly rare outcome if it's all just random chance.
Like winning some kind of cosmic lottery against unimaginable odds.
That's the analogy often used, yeah. An unimaginable lottery. Think about it like this. Chart all the possible values for, say, the strength of the force holding atoms together. The range of values that allows stars to form and life to exist is often just a tiny, tiny sliver on that chart, almost invisible. Pick numbers at random. You're almost certain to land outside that sliver, in the sterile universe zone.
And you mentioned it's not just the constants, the ingredients, but the initial setup, too. The sources really hammer this point. Fine-tuning goes right back to the Big Bang itself. The initial conditions had to be perfect.
Absolutely. It wasn't just about having the right laws of physics. The starting state of the universe was also critical. We're talking about things like the overall smoothness of the very early universe and the distribution of matter and energy right after inflation.
Smoothness. Why does that matter?
Well, if the early universe had been perfectly, absolutely smooth with no variations in density at all, gravity would have had nothing to grab onto. Nothing would clump together, ever. Just uniform expanding gas.
Okay, so no stars, no galaxies. But what if it was too lumpy?
That's the other side of the coin. If the initial density variations were too large, too lumpy, those dense regions would have collapsed under their own gravity almost immediately. They'd form massive black holes long before stars or galaxies had a chance.
So we needed Goldilocks lumps, just the right amount of variation.
Exactly. We need these incredibly small, specific density perturbations, tiny ripples in the fabric of spacetime. These acted like seeds for gravity to work on over millions and billions of years, pulling matter together to form the first stars and eventually galaxies.
And those ripples came from quantum fluctuations.
That's the standard picture, yes. Tiny quantum fluctuations from the very earliest moments, stretched to cosmic scales by inflation. But the amplitude of those fluctuations had to be just right. Too small, and you get a featureless void. Too large, and it's all black holes. Again, a very narrow window for structure formation.
Wow. Okay, so the recipe, the initial mix, both incredibly specific. Let's dive into the ingredients themselves then, the four fundamental forces. You said they govern everything. If gravity sets the stage, maybe electromagnetism provides the actors, but they need perfect timing.
That's a fair analogy.
Yeah.
And yes, the four known forces are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force.
Just to recap quickly, gravity long range pulls galaxies together, electromagnetism chemistry, light, charges, strong force holds nuclei together, weak force nuclear reactions, decay.
Correct. And the universe's stability, its ability to form complex structures, hinges on this delicate balance between the strengths of these forces. Physicists often talk about something called coupling constants. Think of them as dials controlling how strongly each force interacts. And critically, it's often the ratio between these strengths that matters most. Not just the absolute value of one force, but how it compares to the others.
Right. Let's start with gravity. It feels powerful to us, but you're saying it's actually the weakest.
By far the weakest, yes. But it's long range and always attractive, so over cosmic scales, it dominates structure formation, it shapes galaxies, clusters, the whole cosmic web.
So what happens if we imagine tweaking that gravity dial a little bit stronger?
Slightly stronger gravity. Disaster. The entire universe would have reversed its expansion very early on. Instead of expanding for billions of years, it would have collapsed back in on itself in what's called a big crunch, maybe just moments after the Big Bang.
So no time for stars, planets, life, anything. Just immediate collapse.
Precisely. A fiery end almost before it began.
Okay, what about weaker gravity?
If gravity were just a bit weaker than it is, the initial expansion of the universe would have overwhelmed it. Matter would have dispersed too quickly. Those initial density ripples wouldn't have been enough for gravity to pull things together effectively.
So no clumping.
No clumping,
Yeah.
no stars form, no galaxies coalesce. The universe just becomes this eternally expanding, thin, cold soup of isolated particles, featureless and sterile.
That really highlights the importance of that ratio you mentioned earlier, gravity versus the other forces, like electromagnetism, especially for stars.
Absolutely critical. That ratio, the strength of gravity relative to electromagnetism, directly impacts how stars live and die. It sets the timescale for stellar evolution.
How so?
Well, think about a star like our sun. It's a balance between gravity pulling inwards and the outward pressure from nuclear fusion, which is governed by electromagnetism and the nuclear forces. If gravity were relatively stronger, stars would need higher internal pressures and temperatures to counteract it.
So they'd burn hotter.
Much hotter and much, much faster. They'd rip through their nuclear fuel incredibly quickly. Meaning a star like the sun might only live for, say, millions of years instead of 10 billion years.
Not nearly enough time for complex life to evolve on any orbiting planets.
Exactly. Billions of years of stability seem necessary, and that requires gravity to be weak compared to the other forces.
And if gravity were relatively weaker?
Then the inward pull might not be enough to generate the intense pressures and temperatures needed to ignite nuclear fusion in the first place.
So no stars light up at all.
Potentially, or only very feeble ones. You need that stable long-term burning, and that demands this incredibly precise ratio between the force pulling matter together and the forces driving the nuclear furnace inside.
Mind-boggling. Okay, let's move to electromagnetism. The force of chemistry, light. Basically, the architect of complexity.
You can definitely call it that. It governs interactions between charged particles, so it dictates atomic structure, chemical bonds, how light interacts with matter. Pretty much all of biology and chemistry rests on it.
So let's tweak the dial for EM. What if it were a bit stronger, say just a few % stronger?
If electromagnetism were stronger, the repulsion between positively charged protons within an atomic nucleus would increase. Remember, like charges repel.
Right, the Coulomb barrier.
Exactly. A stronger EM force means a higher, harder to overcome Coulomb barrier. This makes it much more difficult for nuclear fusion to occur in stars.
Especially for creating heavier elements.
Yes. It would severely hinder the fusion processes that build elements beyond hydrogen and helium. You might end up with a universe where the periodic table effectively stops very early on. Maybe only hydrogen and helium exist in abundance.
Which means?
No carbon, no oxygen, no iron. None of the heavier elements needed for planets, rocks, or life as we know it. Complex chemistry becomes impossible. You're stuck in this light element poverty trap.
Okay, flip side. What if EM were weaker?
If electromagnetism were weaker, the attraction between the positively charged nucleus and the negatively charged electrons orbiting it would also be weaker.
So the electrons are held more loosely.
Much more loosely. This would fundamentally mess up the stability of electron shells and orbitals, which are governed by quantum mechanics and the EM force.
And that affects chemical bonds.
It destroys them, essentially. Chemical bonds rely on the sharing or transfer of these electrons in stable configurations. If electrons are too loosely bound, you can't form stable molecules.
So things like DNA, proteins, even what?
They couldn't form or would be incredibly unstable. The very building blocks of complex structures, let alone life, would dissolve. The chemistry just wouldn't work.
Wow. So again, a knife edge. Stronger EM prevents heavy elements. Weaker EM prevents molecules.
Precisely. You have to thread that needle perfectly for complex chemistry to be possible.
Okay, let's zoom in even further. Down into the nucleus itself, the nuclear forces. Strong and weak.
Let's start with the strong nuclear force. As the name suggests, it's the most powerful force we know, but it only acts over incredibly short distances, basically within the atomic nucleus.
And its job is?
Its main job is to overcome that huge electromagnetic repulsion between the protons crammed together in the nucleus. It's the cosmic glue, holding protons and neutrons together. Without it, nuclei heavier than hydrogen wouldn't exist.
So crucial. What if we tweak its strength? The sources mention an astonishingly small margin here.
They do. It's perhaps one of the most dramatic examples. If the strong nuclear force were just 2% stronger than its observed value,
Only 2%.
just 2% stronger, the consequence. In the very early universe, nuclear fusion would have been wildly efficient. So efficient that virtually all the hydrogen would have fused almost instantly into helium and perhaps heavier elements right after the Big Bang.
Wait, all the hydrogen gone? What does that mean?
Two catastrophic things. First, hydrogen is the primary fuel for long-lived, stable stars like our sun. No hydrogen fuel, no stable stars burning for billions of years.
In second.
Second, hydrogen is a key component of water. H0. No hydrogen, no water. You simultaneously eliminate the energy source for stars and the primary solvent thought necessary for life.
Just from a 2% tweet upwards. Incredible. What about weaker?
If the strong force were about 5% weaker,
Still a small change.
tiny change, huge consequence. If it were 5% weaker, the binding energy it provides would be too feeble. It wouldn't be strong enough to hold even two nucleons together stably against repulsion or thermal disruption.
Meaning?
Meaning no elements heavier than hydrogen could form at all. Protons and neutrons wouldn't stick together. The universe would consist almost entirely of isolated hydrogen atoms.
A universe of just one element?
Essentially, yes.
Oh.
No periodic table, no chemistry beyond hydrogen, no complexity possible. That narrow window between about -5% and +2% of its current strength basically dictates whether you get a diverse periodic table or just hydrogen.
That's profound. Okay, what about the other nuclear force? The weak nuclear force. It sounds less important.
It sounds less important, but it's absolutely crucial for stellar processes and element creation. It governs certain types of radioactive decay, like beta decay and interactions involving neutrinos.
Beta decay. That's involved in the sun's fusion, right? Converting protons to neutrons.
Exactly. The first step in the main proton chain reaction that powers the sun relies on the weak force to turn a proton into a neutron. So it's fundamental to how stars shine.
Okay, so what if the weak force were stronger?
If the weak force were significantly stronger, again, fusion processes in the early universe would have been too efficient. Much like the stronger strong force scenario, it could lead to nearly all hydrogen being converted into helium very early on, starving future stars of fuel.
So another way to prevent long-lived stars.
Yes. But perhaps the most critical role of the weak force's specific strength comes later, in the death of massive stars, supernovae.
Supernovae, the explosions that spread heavy elements.
Precisely. They're the universe's distribution mechanism for elements heavier than iron, elements forged during the explosion itself, or in the star's final stages. Think gold, zinc, iodine stuff, essential for planets and biology.
And the weak force is key to the explosion itself.
It's deeply involved in the core collapse mechanism. When a massive star runs out of fuel, its core collapses catastrophically under gravity. The immense pressure forces protons and electrons to merge, forming neutrons and releasing a vast flood of neutrinos. This process, inverse beta decay, or neutronization, is mediated entirely by the weak nuclear force.
Okay, so it creates neutrons and neutrinos. How does that cause an explosion?
That sudden formation of a superdense neutron core halts the collapse abruptly. The infalling outer layers crash onto this hard core and rebound, creating a powerful shock wave. But the shock wave often stalls. What re-energizes it, blowing the star apart, is that incredible burst of neutrinos created via the weak force. The weak force dictates how these neutrinos interact with the matter behind the shock wave. If the weak force were much weaker.
The neutrinos wouldn't interact enough.
Exactly. The neutrino interactions wouldn't be strong enough to push the shock wave outwards effectively. The explosion would fizzle. The star would collapse into a black hole, trapping all those vital, heavy elements inside.
So no supernovae, no distribution of elements like iodine or zinc needed for life.
Correct. A weaker weak force means a universe potentially lacking the diverse elements required for complex life and rocky planets. Its strength is tuned just right to allow stars to shine and explode properly.
This is just layer upon layer of precision, from the forces governing stars and atoms. Now let's scale up. We have to talk about the absolute champion of fine-tuning examples, the one that causes physicists the most headaches, the cosmological constant.
Ah, yes. Lambda, the energy density of empty space itself.
Which we now understand as dark energy, this mysterious force causing the universe's expansion to accelerate.
That's the one. And the fine-tuning required for lambda is, well, it's legendary. The observed value is so incredibly small compared to theoretical expectations. The required precision is usually quoted as 1 part in 10 to the power of 120.
One, with 120 zeros after it.
I remember that analogy you mentioned earlier, throwing a dart across the observable universe.
And hitting a bullseye the size of a single atom.
Yes.
That's the kind of mind-boggling accuracy we're talking about. But why is it so problematic? What's the theory that predicts a different value?
The problem comes from our best theory of particles and forces quantum field theory, QFT. QFT predicts that empty space shouldn't be empty at all. It should be seething with virtual particles constantly popping in and out of existence. These fluctuations should contribute energy to the vacuum.
Okay, vacuum energy.
Exactly. When physicists try to calculate the expected energy density from these quantum fluctuations using QFT, the number they get is enormous. It's about 10 to the 120 times larger than the tiny value we actually observe for the cosmological constant.
Wait, 120 orders of magnitude wrong.
Yes, it's often called the worst prediction in the history of physics. It's a catastrophic failure of our current understanding. This is the vacuum catastrophe.
So theory predicts this huge energy density, but we observe something almost zero.
Precisely. It implies that there must be some unknown physical mechanism that cancels out almost all of this enormous predicted vacuum energy, leaving just this tiny, tiny residual amount that drives cosmic acceleration. The fine-tuning isn't just that the observed value is small, it's that it seems to require an almost perfect cancellation between potentially huge contributions. That's the deep mystery.
And the consequences if it weren't canceled. If lambda were closer to the theoretical prediction or even just slightly different from its observed value.
Total, immediate catastrophe, as you said earlier. If the cosmological constant had a slightly larger positive value, meaning dark energy was a bit stronger, the repulsive force would have been overwhelming from the start. It would have ripped the universe apart incredibly quickly. Space would expand so fast that gravity never gets a chance. No structure formation, no galaxies, no stars, no planets, just diffuse gas flying apart.
And if it were negative or more negative?
If lambda had a slightly larger negative value, it would act as an attractive force, effectively adding to gravity on cosmic scales. This would cause the universe to collapse back in on itself almost immediately after the Big Bang. Another big crunch scenario, just like if gravity itself were too strong.
So the very existence of large-scale structures like galaxies and the billions of years the universe has been around hinges entirely on this constant being absurdly close to zero.
That's exactly right. It has to be balanced on this infinitesimal point between immediate collapse and explosive disintegration.
Let's go back down to the particle level again. It's not just the forces, but the properties of the particles themselves, right? Like their masses.
Yes, the relative masses of fundamental particles are also critical. A key example is the ratio of the proton's mass to the electron's mass.
The proton is much heavier, isn't it?
About 1,836 times heavier. Now, if this ratio were significantly different, it would mess up fundamental aspects of atomic physics and chemistry.
How so? Say, if the electron were heavier, closer to the proton's mass.
Quantum mechanics tells us that the size of electron orbits around a nucleus depends inversely on the electron's mass. A much heavier electron would mean much smaller electron orbits.
So atoms would shrink.
Dramatically. And this would have profound consequences for chemistry. The way atoms bond relies on the spatial arrangement and overlap of these electron orbitals. If atoms were much smaller, it would likely hinder the formation of complex, large molecules with specific 3D structures, like proteins or DNA. The geometry required for biology might become impossible.
So the scale of atoms matters for building complex stuff.
It seems to. But perhaps even more exquisitely tuned is the difference in mass between the neutron and the proton. They're very close, but not identical.
The neutron is slightly heavier, right?
Just slightly, by about 0.1%. A tiny difference. But if it were the other way around, if the proton were slightly heavier than the neutron,
What would happen?
if the proton were heavier, it would become unstable. It could decay into a neutron, a positron, an anti-electron, and a neutrino. This is called inverse beta decay.
An unstable proton. What does that mean for, everything?
It means stable hydrogen atoms couldn't exist. A hydrogen atom is just a proton nucleus with an electron orbiting it. If the proton itself decays, then hydrogen, the most basic element, disappears.
No hydrogen means?
No fuel for stars like the sun, no water. The fundamental building block of cosmic chemistry and stellar energy vanishes. The only stable nuclear particle might be the neutron. You'd end up with a universe of neutron stars and maybe some helium, but nothing capable of forming the complex structures needed for life.
So that tiny 0.1% mass difference, making the neutron just slightly heavier, is literally the reason hydrogen exists, stars shine, and water can form.
It appears that way. It's another one of those staggering coincidences.
Which brings us perfectly to maybe the most famous coincidence of all, especially for carbon-based life. The carbon resonance, or the Hoyle state. This isn't just a constant being the right value, but a specific energy level needing to be in exactly the right place.
Precisely. This one is often presented as the smoking gun for fine-tuning, because it involves a very specific prediction made before it was observed. We know carbon is essential for life as we know it, but carbon wasn't made in the Big Bang. It had to be forged later, inside stars.
In giant stars, right, through something called the triple alpha process.
Yes, in the cores of aging giant stars where temperatures hit over 100 million Kelvin. Alpha particle is just another name for a helium-4 nucleus. 2 protons, 2 neutrons. The process itself is already a bit tricky. First, 2 helium nuclei fuse to form beryllium-8.
Okay.
But beryllium-8 is incredibly unstable. It decays back into 2 helium nuclei in about 10 to the minus 16 seconds. An unbelievably short time.
So it falls apart almost instantly. How do you build carbon then?
For carbon-12 to form, a third helium nucleus has to hit that fleeting beryllium-8 nucleus during its incredibly brief existence. This is sometimes called the beryllium bridge. It requires very high densities and temperatures for that third helium to arrive in time.
That already sounds improbable, like threading multiple needles at once.
It is. But the real kicker, the part that requires fine-tuning, is what happens when that third helium nucleus hits the beryllium-8. For the 3 particles, effectively the beryllium-8 and the third helium, to fuse efficiently and form a stable carbon-12 nucleus, their combined energy must precisely match a specific excited energy level or resonance within the carbon-12 nucleus itself.
A resonance, like hitting a specific musical note, makes a glass vibrate?
Exactly like that. If the incoming energy matches this natural frequency, this resonance state of carbon-12, the reaction rate is boosted enormously. If the energy doesn't match, the reaction barely happens.
And this specific energy level is the Hoyle state.
That's the one. It was predicted by the astrophysicist Fred Hoyle back in the 1950s.
And the story is he predicted it because we exist, right? He realized carbon must be made somehow.
That's the amazing part of the story. Hoyle was actually a proponent of the steady-state theory, a rival to the Big Bang, and famously skeptical of anything suggesting design. But when he calculated the rates of nuclear reactions in stars, he realized the standard processes couldn't produce the amount of carbon we see in the universe, which is obviously necessary for life. He reasoned that there must be an undiscovered resonance level in carbon-12 at almost exactly the energy produced by the beryllium-8 plus helium collision to dramatically speed up the reaction.
He predicted it based on the necessity for carbon. And was it found?
It was. Experimental nuclear physicists looked for it and found the Hoyle state exactly where Hoyle predicted it needed to be, around 7.65 mega-electron volts.
Okay, so how finely tuned does this resonance have to be?
The calculations show that if this Hoyle resonance energy level were just 1% lower or even maybe 0.5% higher,
Tiny amounts.
the rate of carbon production via the triple alpha process would plummet by factors of hundreds or even over 1,000.
Meaning not enough carbon would be made in stars?
Not nearly enough. We'd live in a universe essentially devoid of carbon. No organic chemistry, no life as we know it. Forget pencils, forget trees, forget us.
And this is what led Hoyle to make that famous quote.
It certainly shook him. He later wrote something like, "A common-sense interpretation of the facts suggests that a superintellect has monkeyed with physics as well as with chemistry and biology." It was the sheer improbability of this resonance being exactly where needed that struck him so forcefully.
But the fine-tuning for life's elements doesn't even stop there, does it? We need carbon, but we also need oxygen.
Correct. The story continues. Once carbon-12 is formed, it's possible for it to capture another helium nucleus, alpha particle, to become oxygen-16. Oxygen is also vital for life, water, respiration, etc. So we need a good amount of oxygen too.
But if that reaction carbon plus helium makes, oxygen is too efficient.
Then all the carbon produced via the Hoyle state resonance would be immediately converted into oxygen. You'd end up with lots of oxygen, but very little carbon left over.
So you trade a carbon shortage for an oxygen surplus, but still no basis for complex organic molecules.
Exactly. For life as we know it, you need significant amounts of both carbon and oxygen to exist, coming out of stars.
So how does the universe manage that? Another resonance trick.
It's almost the opposite this time. There is an energy level in oxygen-16 that could potentially act as a resonance for the carbon plus helium reaction. But crucially, this relevant energy level in oxygen-16 is located just below the combined energy of carbon-12 and helium-4 at typical stellar core temperatures.
Just below, meaning it's not a perfect match.
Right. It's slightly off resonance. This makes the conversion of carbon into oxygen possible, but relatively inefficient. It happens, but not too quickly.
So it acts like a bottleneck, slowing down the destruction of carbon.
Precisely. It's another delicate balance. The Hoyle state resonance dramatically boosts carbon production. The slight off-resonance in oxygen slows down carbon destruction. The net result is that stars produce and eject substantial quantities of both carbon and oxygen, the two most essential elements for life, into the interstellar medium, ready to form new stars, planets, and eventually, us.
It's like a two-stage fine-tuning, just for the elements of life. First, make carbon efficiently, then carefully preserve enough of it while making oxygen.
That's a very good summary of it. The Hoyle state and the oxygen near resonance work together in this incredibly orchestrated way.
Okay. We've laid out some pretty compelling evidence. The forces, the constants like lambda, the particle masses, the nuclear resonances, it all points to this incredible, seemingly improbable precision. So the billion-dollar question, or maybe the 10 to the $120 question. Why? Why is the universe like this? This pushes us firmly into the territory of explanations, and the big one that often comes up is the anthropic principle.
Yes, the anthropic principle is really a framework for thinking about this apparent fine-tuning, specifically by considering our own existence as observers within the universe. It generally comes in two main flavors: the weak anthropic principle, WAP, and the strong anthropic principle, SAP.
Let's start with the weak one. That's less controversial, right?
Much less controversial. The WAP is basically a statement about selection bias. It says that the conditions and constants we observe in the universe must be compatible with the existence of intelligent observers like us, simply because if they weren't compatible, we wouldn't be here to observe them.
So it's like saying, of course the universe looks fine-tuned for life we're alive, looking at it. We could only exist in a universe that allowed us to exist.
Exactly. We shouldn't be surprised to find ourselves on a planet with liquid water, orbiting a stable star, in a universe old enough for evolution to occur. Those are preconditions for our existence.
It doesn't explain why the constants have those values, just that if we are here, they must have those values.
Correct. It's more about understanding the limitations on what we can observe, based on the fact that observation requires observers. It turns the problem around, in a way.
Okay, that makes sense as a kind of logical filter. What about the strong anthropic principle, SAP? That sounds more purposeful.
It is significantly more speculative and, frankly, more philosophically loaded. The SAP suggests something deeper. In some formulations, it posits that the universe must have properties that allow life to develop within it at some stage in its history.
Must. As in, there's some underlying law or principle compelling the universe towards life.
That's the implication in its stronger forms, yes. It hints at a universe that is somehow oriented towards the emergence of complexity and consciousness. This version is obviously much harder to justify scientifically and borders on teleology, the idea of inherent purpose.
Right, that feels like a very different kind of claim. So if we're not comfortable with the SAP's implications, or if we find the WAP merely descriptive rather than explanatory, what are the other options?
Well, if you want a potential scientific explanation for the fine-tuning, one that avoids purpose, but still addresses the sheer improbability. The leading contender right now is the multiverse hypothesis.
The idea that our universe isn't the only one.
Exactly. The multiverse proposes that our observable universe is just one small part, one bubble or pocket universe within a much vaster, perhaps infinite cosmic landscape.
And the key is that these other universes might have different physics.
That's the crucial part of the hypothesis relevant to fine-tuning. In this larger multiverse, the fundamental constants, the particle masses, maybe even the number of dimensions, could vary from one pocket universe to another.
So they all roll the dice with different settings.
Effectively, yes. You have this enormous ensemble of universes, each with a random set of physical parameters generated by some underlying process, maybe related to string theory or eternal inflation.
And purely by statistics if you have enough universes.
Then it's no longer improbable, but statistically likely, perhaps even inevitable, that some universes within that vast collection will happen, just by chance, to have the right combination of constants and conditions necessary for complexity in life to emerge.
And we naturally find ourselves living in one of those rare life-permitting universes because we couldn't exist anywhere else.
Precisely. It leverages the weak anthropic principle, selection bias, but provides a potential physical mechanism, the vast number of other universes, to make the improbable probable. It turns our universe from being an unbelievable fluke into just one draw from a massive cosmic lottery where all numbers eventually come up.
So the multiverse solves the probability problem, but it comes with its own set of challenges and criticisms, doesn't it? The sources were quite clear on the ongoing debate.
Oh, absolutely. The multiverse is far from universally accepted, and there are significant criticisms.
What's the first major one? Maybe that the fine-tuning isn't real in the first place.
That's a key scientific counterargument. The entire fine-tuning problem rests on the assumption that the fundamental constants we observe could have been different, that they are, in some sense, arbitrary or random inputs.
But maybe they're not.
Exactly. Perhaps there's a deeper, more fundamental theory, a true theory of everything, TOE, that we haven't discovered yet. And within that complete theory, the values of all the constants, the strength of gravity, the mass of the electron, lambda, etc., are uniquely mathematically determined. They have to have the values we observe because of some underlying physical principle or symmetry.
So if a future theory, like a completed string theory or something else, calculates these constants from first principles,
Then there's no fine-tuning problem to solve. The constants aren't tuned any more than the ratio of circle's circumference to its diameter. Pi is tuned. They are fixed, necessary consequences of the underlying laws. The appearance of tuning is just an illusion caused by our incomplete knowledge.
that would certainly dissolve the mystery. What's another line of criticism? Something about changing multiple constants.
Yes, this is the compensating constants argument, or exploring the larger parameter space. Most fine-tuning arguments work by asking, what happens if we change just this one constant, keeping everything else fixed? And often, disaster strikes.
Like our examples, change only gravity or only the strong force.
Right. But that's a very limited way to explore the possibilities. What if you change multiple constants simultaneously? It's conceivable that a universe where, say, gravity is much stronger could still allow for some form of complex structure or even life if perhaps the strong nuclear force was also significantly different in just the right way to compensate.
So maybe the life-permitting zone in the multidimensional space of all possible constants is actually much wider than we think.
It's possible we might be looking at a narrow slice through a much larger region. Physicists have explored some poi models where changing multiple parameters allows for universes that look very different from ours, but could still, in principle, host complexity.
Perhaps supporting life based on different chemistry or structures altogether.
Exactly. We're naturally biased towards looking for conditions suitable for our kind of carbon-based, water-dependent life. The conditions for any form of complexity might be broader. Calculating that full parameter space is incredibly difficult, though.
Okay, that challenges the narrowness claim. What about the big philosophical or methodological objection to the multiverse itself?
The biggest one is testability, or rather the lack thereof, falsifiability. By their very nature, these other hypothetical universes in the multiverse are causally disconnected from ours. They exist beyond our cosmic horizon, potentially with different laws.
Meaning we can never observe them directly or interact with them.
That's the standard view. We can't receive signals from them, we can't travel to them, we can't do experiments on them. Their existence is inferred as a possible explanation for fine-tuning, but not directly verifiable.
And that's a problem for science.
For many scientists, yes. A cornerstone of the scientific method is that hypotheses should be testable, at least in principle. They should make predictions that can be checked against observation or experiment, and crucially, they should be falsifiable. There should be some conceivable observation that could prove the hypothesis wrong.
But if you can't observe other universes, you can't test or falsify the multiverse hypothesis.
That's the core criticism. Some argue that if a concept is inherently untestable, it steps outside the realm of empirical science and becomes metaphysics or philosophy. While it might be a logically possible explanation, it's not strictly speaking a scientific one in the traditional sense.
So it solves one problem, improbability, but creates another, untestability.
That's a good way to put it. The debate continues on whether indirect evidence or theoretical consistency could count as sufficient support, but the lack of direct testability is a major hurdle for the multiverse idea.
It really leaves us in a fascinating, if maybe frustrating place. We have this data showing incredible fine-tuning, from the cosmological constant needing that 1 in 10 to the 120 precision, to the strong force needing to be within just a couple of percent, to the Hoyle state resonance needing to be perfectly placed for carbon.
The evidence for apparent fine-tuning across multiple scales is compelling.
And the explanations on the table seem to be: 1, it's just incredible luck, made plausible only if our universe is one among a near-infinite number, the multiverse.
That's the chance hypothesis, amplified by the multiverse.
2, it's not luck at all. There's a deeper physical necessity we haven't found yet, a theory of everything fixing the constants.
The necessity hypothesis, appealing to future physics.
Or 3, we're misunderstanding the question because of observer bias, the weak anthropic principle.
The selection effect explanation.
Each one feels plausible in its own way, but they can't all be right.
And that's why this remains such a profound mystery. It sits right at the intersection of cosmology, particle physics, and deep philosophical questions about reality, chance, and necessity. It genuinely forces you to confront your assumptions. When you see numbers like 1 in 10, 120, or the razor-thin margins for the nuclear forces, the immediate human reaction is often, well, it feels like it can't be random chance in a single universe.
Like Hoyle's reaction, it looks monkeyed with.
Exactly. But is that feeling just a failure of our intuition to grasp truly astronomical odds, which the multiverse could provide? Or is it a valid intuition pointing towards an underlying structure or law we don't yet comprehend?
Or something else entirely.
Or something else entirely. What does it mean for our existence to hinge on these seemingly arbitrary numbers? Does it limit the power of physics to explain everything from first principles? Or does it point towards the ultimate triumph of physics when we finally understand why these numbers must be what they are?
A final thought to leave our listeners with, then.
Maybe just to reflect on that tension, the universe appears exquisitely fine-tuned for complexity, for life. Is that appearance simply a cosmic coincidence amplified by a vast multiverse? Is it a signpost towards a deeper, necessary physical law? Or does it hint at something about the relationship between existence and observation that we haven't fully grasped? Pondering Hoyle's initial reaction, luck, necessity, or something more really gets to the heart of one of the biggest questions we can ask about our place in the cosmos.